This is Chapter 16, Lecture 1, Streams and Flooding. Our goals for this chapter include to better understand the processes associated with streams, such as erosion and deposition of sediments. We will also look at the different features of streams, which include meanders, floodplains, and deltas. And then we'll investigate the importance of streams to society in terms of things like flooding. We'll start with a satellite view of the Yukon Delta. So there's a few obvious features we can see. To start, there's many lakes and wetlands throughout, right? That's the dark blue parts. And we have what's called a distributary system of like rivers and streams that are actually discharging to the Bering Sea. There's a bulge of sediment along the coastline, that's our delta. There's more vegetation on the delta, and then there's lighter colored water, which is rich with sediment along the coast. Okay, so thinking about the Yukon River drainage area, and the Yukon Delta was where we were just looking, kind of a different orientation now. We have this whole huge network of rivers and streams that feed into the Yukon River and then ultimately discharge and deposit the Yukon Delta. It's just a really large area. And this is meant to kind of just show you the difference in drainage basins. So you can see the red and blue areas and their boundary. This is one drainage basin, and this is an entirely separate one. So the red area is drained by one stream, and the blue area is drained by another. Again, each of those is a drainage basin. And here's our drainage divide between the two. Okay, now we're looking at the volume of flow in a river system versus time. All right, so the plot of discharge versus time is called a hydrograph. So you have discharge here and then time. We have a storm event. A lot of rain precipitation was introduced to this area. That causes the stream to reach peak discharge at a certain time, and then it'll sort of taper off after the storm event. So the hydrograph shows flow increasing during a flood event, really, and then decreasing as the flood ends. And then this one can represent runoff that we'd see in a basin with very steep slopes. You'd get a big peak here that tapers off quickly, it drains quickly, versus a flooding event in a basin with gentle slopes would be more gradual. So we want to understand that in a gentle sloped system, we're going to have our discharge spread out over time, and there'd be less peak flow as opposed to a basin with steep slopes. Okay, so more on these hydrographs. All right, so we have a simple drainage basin. Not a lot of complexity to how the water flows through that drainage basin. We find that runoff reaches the main drainage areas in an orderly way, and it's going to look like that. The hydrograph's going to look like that. It's simple. But imagine a more complex basin shape. Water can then show up at different times because we have different geologic features here, and the black arrows indicate flow of water. So we're going to see a hydrograph that has more peaks due to the complexity here. Now, when the time when the water arrives depends on the distance it has to travel and its rate of flow, and that also hints at different sizes of streams as well. Okay, let's talk about tributaries, and those are the smaller streams that feed into larger streams. They're smaller subsidiary channels. All right, and we have to introduce the concept of stream drainage order. Okay, so in a dendritic tree-shaped stream system, we can number the different tributaries as such. The first one that we see has a stream order of 1. That feeds into the next branch, or like antlers even, and that's a stream order of 2. You can see there's a corresponding 2 here. And those feed into this channel, and we say that drainage order is 3, and then ultimately it feeds into 4. Okay? And understand that tributaries spread out stream discharge over time. So that's dendritic, like a tree. You can also have radial drainages, and those flow outward in all directions, like off a circular mountain or dome shape. Or you can have structurally controlled drainages that follow tilted or folded layers, faults, joints, or other patterns. And of course, streams can cut across layers or ridges, like in the Appalachian Mountains or something similar to that. These are our North American drainage basins, the major ones. The question is, where would runoff in our area end up? Well, believe it or not, the Great Lakes region, that goes to the Atlantic Ocean ultimately. All right. You have this area. Okay, that all ends up to the south. We talk about the continental divide sometimes. It goes up through Montana. It's generally used to refer to the boundary between drainages that flow to the Pacific versus those that flow to the Atlantic and the Gulf of Mexico. But we have more divides than that. This interior drainage area, it doesn't drain to the sea because it's disrupted by the basin and range area in Nevada and Utah. Okay, so this area does go to Pacific Ocean in green. Up here, we'll drain to the Arctic Ocean. So that's another way of thinking about the lower 48 and parts of Canada and Mexico. All right. So within a stream system, how is material transported and deposited? This is a little cross section. All right. So within, say, a river, you have fine particles. They can be carried in suspension. They can float in water. And this other stuff, you can have soluble ions dissolved in and carried as well by moving water. More excitingly, sand grains can roll and bounce along the bed or the surface of the sediment on the bottom of the stream. Cobbles and boulders, they can mostly roll and slide during high energy, high flow events. But all this material moving is called the bed load. If they bounce, if these grains bounce, we call that saltation. Okay, so what processes erode material within a stream bed? Well, these sediments can be picked up by turbulence and low pressure caused by moving water. So you get sometimes little circular movements within that pick up materials and erode the bed further. And then moving clasts can collide with other clasts and obstacles, which then chip away or launch more pieces. And then turbulence loosens and lifts pieces of the stream bed as well. Soluble material is going to be dissolved and removed. Let's look at turbulence a little closer. Okay, so remember that viscosity is the resistance of something to flow. So viscosity and surface tension actually act to keep water smooth, as in slow moving water is pretty smooth. But moving water It does have some inertia. It tries to keep moving with the same speed and direction. Okay, but at higher velocities or near obstacles such as sediments or rocks, flow becomes more chaotic and turbulent. We see these sort of circular movements that can form a swirl that we call an eddy. And then upward flowing eddies can pick up loose material. Okay, let's think about stream gradient. So this is showing you a slope, and assume a stream is flowing down the slope. All right, so our steepest gradient on this figure is 15 meters per kilometers. And gradient, that's our change in elevation for a horizontal distance, shown by these small blue triangles. And it's usually expressed as meters per kilometer or feet per mile. And so our steepest gradient is up top, right? And then the gradient goes down over time. With a steeper gradient, the stream drops more for a given distance. So with that, how does a stream change downstream? We have T1 through T3 marked as tributaries, H being the headwaters where that stream originates, D being the delta, and then M being the mouth, essentially where the stream ends. So there's a lot of different charts for this slide, but we'll start here. So we have essentially an increase in discharge with an increase in channel size, if you looked at that in cross section. Also, as you get from the headwaters to the delta to the mouth, you're going to have an increase in water velocity as everything feeds in together, or flow velocity. It's not really intuitive that water velocity increases downstream. It appears that velocity would be higher in steep mountain streams, but actually turbulence slows the average rate of water velocity. So that's something to think about. All right, discharge as well is more intuitive. That will increase as you go from the headwaters through each tributary through the delta to the mouth. We have all this water added together. And then our total stream load keeps going up as we head toward the delta, but it's deposited at the delta and we see very little at the mouth because all this energy is dissipated at this larger body of water. And then our maximum sediment grain size is highest at the headwaters and goes way down as you get to the mouth. Okay, so sediment size versus current velocity. We have velocity here, and then sediment size, silt and clay here, then sand and gravel. The silt and clay is the lightest. Of course, it's mostly going to be suspended sediment. It's transported. The bed load is going to be maybe a little bit of silt and clay, but mostly sand and a little bit of gravel. And then what's deposited, the heaviest stuff, under low velocity especially, is going to be sand and gravel. And the main point of this graph is that how sediment is carried, or even if it's picked up, depends on stream velocity. And different sediment sizes can be carried by different mechanisms depending on the stream velocity. So to review that, at high velocity, the smallest particles are carried in suspension. Moderate velocity has silt and clay suspended, but sand's going to be bed load, rolling around or saltating. And then at our lowest velocity, sand is dropped, but silt and clay remain in suspension, and of course gravel isn't really going to move very much. So how can streams vary over time? This is discharge versus seasonal changes. Our peak discharge in this, say, North American stream, we see this in the spring. The most water is in the spring. You'll find that if you go out in the Rocky Mountains You got a lot of white water in the rivers, and it's dangerous to wade through a lot of them. All right. You have a lot of snow melt feeding into that, so that's a major factor. Okay. And then it'll go down through the summer, but there might be, say, thunderstorms that give you a little bit of a peak. It'll go down. And then in fall, we can have rain, quite a bit of rain. And then it'll go down as this is snow and everything remains frozen. And then repeat the cycle. This is going to vary every year, but we expect something like this. Our smaller fluctuations that we see here can be a record of individual events, like a little storm or an especially warm week that results in more snowmelt. So how do streams change downstream? We've talked about that a bit. This is a profile of the James River in Virginia. We have elevation and then distance from the source. Okay, so streams tend to be steep near their origin, say if they originate in the mountains, right? And then most streams become less steep, more gentle downstream, right? As you go from the Appalachian Mountains, where the headwaters are, to the Piedmont, to the coastal plain. Got a little bump in the middle because it goes back up. I'm not sure exactly what that is. Interestingly enough, the drop from the Piedmont to the coastal plain is at what we call the fall line. Sort of an easternmost extent of the Appalachian Mountains and sediments associated with them. We actually see waterfalls there too. We'll talk more about that later. And base level. The lowest level to which a stream can erode is what we call the base level. It can be a sea, lake, or closed basin. High above the base level, you have a lot of erosion of sediments. Streams can have steeper gradients there and erode sharply into the terrain. And then closer to the base level, you have less erosion. Sea level being the ultimate base level. And then our landscape is going to reflect decreasing gradient and how high above base level the stream is. Kind of the roughness of the landscape. All right, and then we have some curves in streams here to look at. The flow direction of water denoted by these black arrows. So this is a braided on the left. That's a network of interweaving channels. And then a low sinuosity stream. It's gently curved. Meandering stream. It has high sinuosity. It's very curved. So you actually have what's called a cut bank here, where sediments are eroded. Water actually travels faster on this edge, and then a point bar where water's traveling slower and deposits sediment over time. So looking at braided versus meandering streams further, this stream is braided and this stream has meanders. Right, there are some curves to the braided components of the stream. We can see as well here the cut bank and the point bars complementing one another. Over time, meandering streams do become more curved. And what processes operate on those? I already hinted at quite a bit of this, but let's break it down. We've got small graphs that show profiles across the stream channels. So in a straight channel with the meandering stream, we see that's kind of symmetric and it's fastest in the center. Inside a bend, you've got shallower and slower with the point bar. And the outside bend and the cut bank, that's faster because we've got erosion happening there too. Not because, but we do have erosion happening there too. And then erosion and deposition could be balanced in this area, so we're not seeing the point bar and the cut bank together. But how do they form and move? How do meanders form and move? So the curve begins when the water velocity is faster on one side. It gets eroded and deepens, and then the deeper side carries more water, and then the water's faster, so then we have more erosion as well, forming that cut bank. The inside has less water and slower water, so it has deposition, forming that point bar, and then the meander erodes its outside bend, which increases curvature over time, and the meander migrates outward and downstream. Then we see continued erosion or overflow during a flood that can cut off a meander and then form what's called an oxbow lake. So we see all those associated with meandering streams. Let's talk about the headwaters of the streams, where we see it originate. Okay, some features associated with that would be a waterfall. And that's where resistant rocks or a tributary valley is higher than the main valley. You could also have a rapid. In this area, you'd have a turbulent river due to an obstruction like debris from a tributary, a landslide, or bedrock in the channel. You might also see a mountain lake. Water could be impounded by some obstruction, or this could be where bedrock is deeply scored, leading into a braided stream. Okay, so this stream drains a steep mountain range with glaciers and an abundant sediment supply. The stream exits mountains with a steep gradient and flows into a sloping plain. And then the sediment-rich stream is braided all the way to the ocean, where it discharges ultimately. And we'll look closer at that. So these braided channels, they have steep gradients, an abundant supply of sediment, and variable flow rates, possibly due to seasonal changes, most likely, yes. And then this is a fairly straight stream. So braided channels might be part of a stream with a fairly straight path. They kind of just look a lot more irregular when you look closer. And with that, we'll look at a low gradient stream. Unlike the braided stream, we're seeing a low gradient here. In this case, we have one main channel that has meanders, point bars, and cut banks. There's also a floodplain with a gentle gradient, flooded only by high flows. And some terraces could form along a gently sloped stream. Those terraces are sort of incised into the floodplains, but we don't have that in this example. We could also have meander scars, cutoffs, and oxbow lakes. This stretch of the Mississippi River is something that's typical of a low gradient stream. It has all the features we previously pointed out for the most part. You've got a meander, a point bar, a cut bank, a cutoff meander, and then meander scars, what used to be there. It also has an oxbow lake. And we will stop here for this particular lecture.